to hit record. Welcome back to Astronomy 1010, the online edition. Nice to have so many of you here. Another important thing that I need to remember to do, I need to go into speaker view, and I need to lock the speaker view on me. Can you guys hear me okay? Chrissy, give me a thumbs up if you can hear me. Okay, awesome. So, our first class on Monday was a bit of a learning exercise for me, and I learned a few things watching the video. The first is for people who are going to be watching later, or for those of you who might want to re-watch later, I need to make sure I keep us locked in speaker view so that you guys can clearly see the notes. Anyone who watched the video that I posted up to Blackboard will notice that for the entire episode, I was in a little tiny box up here in the corner, and it probably made it really infuriating for those of you who wanted to take notes. So anyone who needs to lock their speaker view can just double click whatever person they want locked in their speaker view there. And you guys should have your own switches, but I need to do this because I'm in control of the recording. I also figured out a few glitches that I hadn't worked out last time. I now know I had to reinstall the program, but my iPhone works. That means we're going to be able to do lab today, but we're also going to have to do the last 3 problems in our homework. And I'm hoping we'll be able to do all of that in a timely fashion. So we'll do our normal lecture from now until, about 12:45 or so, and then take a quick break, and then we'll try to crank out lab and do our last 3 homework problems. One last thing that I want to say that I kind of learned from watching the video and analyzing it is it's nice when people share their video. You don't have to, obviously. If you want to be a troll in the background, be a troll. But thank you to those of you who do share the video, because then I can see your little faces and we can interact a little bit that way. It also helps me to know what's going on, like if you guys are squinting or if you're writing. Like in a classroom, I have a lot of cues that I can pick up on to figure out how to make the lecture better. And seeing a few of you, like seeing Laura there with her pencil in hand, makes me very excited. I feel like some serious notes are about to get taken here, right? All right. So in fact, I have a feature. I'm loving the Pikachu, by the way, Thomas. It was just one of the highlights of my watching the video back. I'm gonna do one last thing before I get going here, and I'm gonna go into my settings, and I'm gonna hide the non-video people. They're still able to participate if they want to, but I want to do this so that I can see some of you interacting with me. I just need to figure out where this feature is here. Oh shucks, I had it a moment ago. Video settings, here we go. Okay, so for video, I'm going to, you guys probably can't see this, hide non-video participants. Okay, so that's what I'm doing. That way, even if there's quite a few more of you here, I'm just focusing, hello Tony, I'm focusing on the people I can see because I can interact with you guys a little bit better. Do this. Okay, cool. Okay, so let's think about where we ended off last time. We were just learning about the electromagnetic spectrum, correct? Does that sound like what people remember? All right, I brought with me from CCRI, I brought my prism with me. And this is a prism just like Isaac Newton would have used to separate white light into the component rainbow colors. I have a totally dope demo that I do where I send the 400-watt projector light through the prism, and I can scatter a rainbow right onto the dry erase board. But one of the oversights I made is I didn't steal it turns out that projector is useful to me in a lot of different ways, and I wish I had stolen it. Now I do have a light here. I have an incandescent light, just a second. And I tried this the other day, so this is a very bright light. Unfortunately, you really have to, you've got to collimate your beam, and you've got to get it going through a very narrow slot to do this demonstration. And I did have a box here for this purpose. Okay. Now I tried this a couple of times and it did not work, but I have a new plan here. And we'll see if I can't collimate a beam of light And what my goal is to send a rainbow right into the projector, lens. And I managed to do this the other day, but no. Well, in any case, I probably should have planned that out a little bit better. I need a, normally, I'll show you the animated graphic here. Let's go to our PowerPoint slideshow. I want to open up our PowerPoints. 1020. Here's our light and telescopes. And now I'm going to share my screen with you guys. Bear with me here. I'm still clunky at this thing. Share screen. Just share the whole bloody screen. And we'll go to function F5. Shoot. Click function F5. All right. So let's jump ahead here to our prism. You can see here that when a prism disperses light into its component colors or wavelengths, normally someone has to take a box or some kind of a metal baffle, and they have to cut a very, very narrow slit into the baffle. I tried to do this at home, but my light bulb just wasn't bright enough to pull it off. By cutting a thin slit into a piece of metal or a piece of cardboard, you collimate your light into a beam, and that beam of white light will strike the prism at a very specific angle, dispersing its light into its component wavelength. When you do this, of course, you create something known as the continuous visible spectrum, AKA the rainbow. You guys have called it the rainbow up to now, but from now on, we're going to refer to this as the visible continuous spectrum. I'd like you to sort of accidentally memorize that 400 nanometer wavelength is the color purple, and 700 nanometer wavelength is the color red, and green is somewhere in the middle around 500 or so. I guess technically teal is 500. Like I said, it's a really nice demo to do, but I need a much brighter light source to pull it off. All right, let's exit this and let's get back to our view here. So we're going to try to take some notes on the electromagnetic spectrum and some of the properties of waves. Oh, I want to say one other thing before I forget to say it. Some of you who are in the night class, like Tina and Tony and Laura, you guys did not get a module on energy. And what I think I'm going to do about that is I'm going to record a separate video for energy. I won't make anyone have to log in live for it, but I'm going to post that. I'm trying to post all of our videos both to YouTube and to Blackboard. And that way the module will probably be about 30 minutes long. I'll go through potential energy, kinetic energy, temperature, and I'm even going to do momentum. The day class did not get a lesson on momentum either. So if you care, if you're interested, you'll be able to watch that 30-minute video of me taking some notes. And that way I do right by the night class. So don't let me forget about that, okay? All right. So first of all, let me go back to gallery mode and then speaker view. How do I, sometimes your little faces appear at the top and sometimes they appear on the side. I don't really know how to control any of that, but I guess it's not important because you can see my notes. Okay, so let's take some notes about light. Light, I'm going to kind of bring this closer here, is an electromagnetic wave. How's the readability of this? You guys see that okay? I got some thumbs up here. Thank you very much. Okay. So I think I gave you these notes last time. It's part electric field. It's a wave of electric field energy, and it's a wave of magnetic field energy. Now, electric fields and magnetic fields are related to the force of electromagnetism. You can think of a field as the essence of charginess that surrounds a magnet or that surrounds a charged particle. I've got a couple of magnets over here, Oh, by the way, you'll notice my microphone now should pick up my sound left and right. I have a new microphone that will help with the audio, but the trade-off is there's going to be a bit of crackle in that's my audio problem. It's because I've got a crappy old Logitech camera that I'm using for this. Anyways, here's some relatively potent magnets. And if you've ever taken some powerful magnets and tried to push their two north poles together, you can feel this sort of magical invisible force between two magnets, right? That's the magnetic field. You can't see it, but it is a real physical object. It's a force field, just like out of Star Trek or something like that. The magnetic field is actually associated with moving charges, and the electric field is associated with static or sort of frozen charges. But in any case, they're both related to the force of electromagnetism. We're going to learn a little bit more about magnetic fields when we study the sun, and I'll defer some of my lesson for that. But if we wanted to take a quick moment to look at a physicist's picture, I'll share my screen here. And I can't remember if I showed this to you last time, but in slide 25, you can see here an electromagnetic wave, one part electric field shown in blue, and one part magnetic field shown in red. And what's important is this is a traveling wave. This picture here is frozen, but the wave oscillates. It undulates like a little, like a worm, okay, like an inchworm. It undulates and it travels through space at a finite speed, the speed of light. Here's a sort of more animated graphic of our traveling electromagnetic wave, where you can see the, I guess the electric field is in green here and the magnetic field is in blue. Light is a unique type of wave, but all waves obey a certain set of properties. And class, can you remind me, did we do the properties of waves? Did we write down wavelength, frequency, and energy last time? I vaguely remember doing that.
Yeah, we got even past up to where you were talking about Vibgor. So,
Vibgor?
Yeah.
That's the continuous visible spectrum, right? So I'll try to connect these two things together. So all right, let's talk about Roy-G-Biv, as it's sometimes called, or Vibgyor. Vibgyor is an acronym that has to do with the order of the colors. I'm forgetting my slide numbers here. There's two ways to create a rainbow. A rainbow is sometimes called a dispersion because you're taking white light and you're dispersing it into its component wavelengths. In this animation here, you can see red is at the top, and counting from the top, the order of the colors goes red, orange, yellow, green, blue, indigo, violet. Or Roy-G-Biv is the acronym. That's the mnemonic device to remember the colors. I prefer to do it from the purple side at shorter wavelengths. And when you do that, let's take this as a note. The visible continuous spectrum makes the acronym Vibgyor. And that's just a little mnemonic device. Roy-G-Biv is more popular than Vibgyor, but I like doing it, and I always like to think in terms of increasing wavelength, as I'm more of an optical astronomer than a radio astronomer. So, so 400 nanometers is purple, 700 nanometers is red. But of course, the visible continuous spectrum is just one part of the totality of all the different types of light that there is. Let's just move ahead here and see if we can look at this. Did you guys get to see this picture last time?
Yeah.
You saw this picture. This is an important picture. I need us to sort of memorize. Did we do a note on it? I'm forgetting. Let's take this down as a note if you guys can't remember. So the totality of all the different types of light, I've got to remember constantly to get back to speaker mode here. We have the electromagnetic spectrum. To To understand astronomy, you need to be conversant with the electromagnetic spectrum. It's kind of like the periodic table of elements, except for light. And if I use a ruler here, we can draw out different bands or regimes of the electromagnetic spectrum. In the middle of the electromagnetic spectrum are the types of light that our eyes are sensitive to. This band is the visible regime. Sometimes it's also called the optical regime. And here's where we get our VIBGYOR. Violet, indigo blue, green. Make this jazzy with colors here. I don't have any, I think I have an orange somewhere if I want to get real creative. Oh yeah, baby. I do not have a yellow. Y, O, and last one. How about that? Check out my colorful rainbow moves. You won't just find those rainbow moves in any old astronomy class. I want you guys to know that. Okay, so, of course, here what we are plotting is we're plotting wavelength in nanometers. This is the symbol for wavelength. It's the Greek letter lambda. And we're increasing towards the right-hand side of the electromagnetic spectrum. Your eyeballs are sensitive to a range of electromagnetic radiation that goes from 400 nanometer wavelengths, which you call violet, to 700 nanometer wavelengths, which you call red. But there are so many other types of light besides visible light. If we increase the wavelength, and by the way, let's remind ourselves what wavelength is. I think we did this last time, but if this is an undulating wave, wavelength is a physical length that measures the distance between a repeating cycle of the wave. Or in other words, the distance from crest to crest of your wave. So this distance here is the wavelength lambda. Although you cannot see an electromagnetic wave, it's invisible. Although you cannot see a magnetic field, these waves do represent a physical distance. Sometimes they're measured in tiny units like nanometers. Some types of light, like radio waves, have wavelengths that can be as long as a meter or even the length of a school bus. So let's look at a couple of the other regimes of the electromagnetic spectrum. If we just increase the size of our wavelength past what our eyeballs can detect, we end up in a regime known as the infrared regime, or simply the IR. My cartoon drawing here is sucky in some respects because the visible regime is actually quite narrow, whereas comparatively, the size of the infrared and radio bands are quite large. But because our eyeballs, well, because we have eyes that detect these wavelengths and we discriminate color, we assign an inordinate amount of importance to the visible domain. Infrared light starts a little after 700 nanometers. Sometimes in the long end of the spectrum, we use a unit called microns. 1,000 nanometers is equal to 1 micrometer. That's the Greek letter mu there. I don't know if you guys can see that. Let me put the Greek letter mu nice and big. That's the symbol for micrometer, or sometimes astronomers call them microns. And a micrometer is a millionth of a meter. So it's 10 to the -6 meters. Let's think, do we know our metric system? If I break a meter into 1,000 parts, what's that called? Someone talk to me here so I'm not so lonely.
Millimeter.
That's a millimeter. So how many times would I have to divide a millimeter to get down to a micron?
1,000.
1,000, right. So a micron is 1,000th of a millimeter, and a nanometer is 1,000th of a micrometer. Okay, so infrared starts somewhere around 1 micron, and it kind of goes all the way up to about 1 millimeter. 1 millimeter is approximately the wavelength at which astronomers or physicists decide we've kind of entered a new domain of light, and that is the radio regime. Believe it or not, your cell phones, which you love to use for communication with loved ones and friends, these are little radio infrared, well, they're radio transmitters, and they broadcast a faint radio signal at pretty close to a millimeter. I think it's just a little bit past. So we all have radio light transmitters in our hand when we operate our cell phones. Radio waves are extremely long wavelength, and they're also extremely low energy for reasons which I am going to explain in a little bit. Radio waves can pass right through your body and even the walls of your house as if they were transparent glass. So one of the funny things that we're going to learn about light is light tends to interact with structures and materials that are comparable to the size of their wavelength. So one of the reasons why things like our clothing and our bodies are opaque to visible light is wicked tiny. It's like the size of a virus, right? To be topical, it's 400 to 700 nanometers or so. And those wavelengths are too small to, the structures of our clothing and the molecules that make up our clothing are larger than that. And so light tends to just kind of bounce right off of those structures. But when you get into long wavelengths like radio waves, thank God, I might need a diet, but I'm not quite a meter in thickness yet, right? I am much thinner than a meter. I'm approximately 1/5 of a meter in thickness. So radio waves that are of order a meter long can pass right through my body as if I was transparent glass. That's one of the kooky things about light. Light tends to sort of, if you're smaller than the wavelength of light, it can just sort of pass right through you without much interference. And there's a lot of different aspects of astronomy and optics that depend on these ideas. Let's go over here and check out the shorter end of the electromagnetic spectrum. Now, the fact that I'm yapping about this so much means it's kind of important to me, right? And that means it should be important to you too. If you go shorter than violet, you of course end up in the ultraviolet regime. And ultraviolet starts around 400 nanometers, and it goes all the way down to about 10 nanometers or so. And of course, we don't see ultraviolet light, although black lights can give off a certain amount of ultraviolet light. But you are familiar with going to the beach and getting a sunburn. It's not visible light that gives you a sunburn at the beach. It's ultraviolet light. So that's probably your closest experience with UV. At even shorter wavelengths, we get into two even peskier domains of the electromagnetic spectrum. There are extremely short wavelength X-rays. X-rays are usually, your experience with X-rays is getting medical imaging done at the hospital. X-rays are so tiny that they can pass through the flesh of your body and bounce off of the denser bone inside of you. X-rays are, however, capable of causing mutations in your cells, just like ultraviolet light is capable of giving you a sunburn. X-rays bottom out somewhere around, I don't know if you guys can read this or not, but the cutoff for X-rays is 1/100th of a nanometer. And then you get into the super short wavelength, super dangerous gamma ray territory. Gamma rays are so short wavelength. Gamma ray photons are light of such a tiny wavelength that they almost act more like particles, like little potent BBs, than they act like waves. And they're so short wavelength and so high energy that they can knock out nucleotides in your DNA and basically randomly recode the genetic material in your cells. Here's a hint, that usually doesn't end well. Every now and then you might turn into a Teenage Mutant Ninja Turtle, but for the most part, getting irradiated with gamma rays is a one-stop ticket to cancer and other creepy mutations. Of course, gamma rays are produced not only in nuclear explosions like nuclear bombs, but also in power plants and nuclear power plants and such. Okay, so now you know about the electromagnetic spectrum, and I'm going to ask you to sort of accidentally memorize this because astronomers can learn about astronomical objects by studying light emitted and reflected from objects at all of these wavelengths. And today we're going to take a journey into the world of analyzing light and understanding light so that we can understand what substances are emitting that light. Okay. Can gamma rays turn me into the Hulk? Absolutely. Okay. I don't know if you guys are seeing this chat, but yes, gamma rays can turn you into the Hulk if you're very, very, very lucky. Okay. On the other hand, and you know where some of that stuff comes from, I read a book once. Let me share my screen. This is just a fun aside, or actually a not so fun aside. If you want to read a first person's account of what it's like to be irradiated with a gamma ray blast, you can read a book called Black Rain by Abuse Masuji. I'm going to have trouble spelling that, so yeah. So I don't know how this happened, but I went into an old secondhand bookstore one day, and I found a copy of this book called Black Rain. It's a classic of literature, and it was a short novel by this Japanese guy who had actually survived the atomic blast at Hiroshima. And honestly, it's tragic, mind-blowing, and a heart-wrenching novel. He actually was closer, the people who were closer to the epicenter of the blast actually had a higher chance of survival, because at the epicenter of the blast, somehow the gamma rays kind of propagated out from the epicenter, and the further away from the epicenter you were, the more irradiated people got with these gamma rays, which actually doesn't make sense from the inverse square law point of view. But in any case, he described seeing some pretty crazy things. Like he walked by a koi pond, and somehow mutations had caused the grass along the koi pond to grow at an accelerated rate. So there was all kinds of mutant grasses that were growing like several centimeters every day and looking all weird and strange. That's where people get the idea for the Hulk, that these mutations mostly are maladaptive, but every now and then you can have a spontaneous beneficial mutation, or a mutation that could do some superpower, like turn you into a green crime-fighting superhero. I don't know. It didn't work out so well for any of the people who got hit by these gamma rays, but I suppose it's always probable. You should check out that book if you want a real bum out. It'll really break your heart. Okay, so let's stop sharing the screen before I say anything else douchey. Okay, let's learn a little bit about the properties of waves so we can understand electromagnetic energy. Light are electromagnetic waves, but there are all types of waves in nature. There's waves on a string, there are ocean waves, the sound that the microphone is picking up is also a wave, and all waves share some common properties. I think I put these on the board last time, but let's do it again, let's do it right. Properties of waves. Okay. Probably for an optical astronomer, the single most important property is wavelength. And we already know that wavelength is a code for color. Our eyes discriminate wavelengths as the psychological experience as color. And it's the length of a repeating crest of your electromagnetic wave. The units that we measure wavelength in the MKS system are meters, but it's not uncommon for people to measure wavelengths in nanometers, which are a billionth of a meter, or micrometers or microns, which are a millionth of a meter. Usually when people work in the visible domain, they talk about wavelengths in terms of nanometers. Astronomers who spend their entire careers working in the infrared, and yes, there are astronomers. You know what's kind of cool? You guys are here in my bookshelf with all my favorite undergraduate and grad school books. I worked in a research lab with this guy. He's an authoritative expert on infrared and radio astronomy. Detection of light from the ultraviolet to the submillimeter. Anyways, there are people who spend their entire careers working in the infrared and radio domain. You can do a lot of good astronomy in these bands. Okay, remember that light is a traveling wave, and traveling waves have a frequency. And a frequency, which I use the symbol curvy F for, are basically how many cycles per second my traveling wave has. Cycles are a conceptual unit. It's the number of oscillations. Seconds are a real physical MKS unit. A second is a well-defined construct in physics. But a cycle is kind of like a concept. So you'll see me put the units cycles in quotation marks because they're kind of like dummy units. You can keep them there or you can leave them behind. For instance, it's not uncommon for people to express frequencies as per seconds or 1/seconds. If you see an astronomer write 1/seconds, you should probably put the cycles back in your brain, and you should think, okay, they mean cycles per second. But the actual physical unit is kind of awkward. It's inverted time, 1/seconds. People don't like it when you say things like inverted time. That's the kind of thing that makes people move a couple of bar stools away from you at night, okay? So for that reason, we've invented a new, more friendlier sounding unit called the Hertz. HZ. And Hertz can be thought of as the MKS unit of frequency. 1 Hertz is 1 per second or 1 cycle per second.
Is that like FM radio station frequencies?
Hell yes. And if you want today, Lucas, one of my favorite problems to do when we learn about these wavelength, frequency, and energy is for us to calculate the wavelength of the radio station formerly known as WBRU when it played music that people like to hear. So Lucas, don't let me forget that I want to calculate the wavelength of WBRU. So in the radio regime, radio stations tend to broadcast in megahertz. 1 megahertz is 1,000,000 hertz. And they also broadcast sometimes in the gigahertz regime. 1 gigahertz is 1,000,000,000 hertz. This is kind of like microns and nanometers, except flipped over and inverted, right? Billions and millions. So oftentimes, this is kind of a weird thing. Optical astronomers that work with visible light telescopes, they always talk about light in terms of wavelength. But if you go to a conference by astronomers and you're just talking to a bunch of radio astronomers, none of them will talk about the wavelength of light that they're detecting. They only talk about light in terms of frequencies. And to make it even weirder, when you go to particle physics conferences where people talk about super short wavelength X-rays and gamma rays, they don't express photons in terms of wavelength. They don't express photons in terms of frequency. They talk about photons in terms of energy. It's just like, it's tribal. That's the only way I can explain it, okay? And these are just customs that each of these astronomer tribes obey, and you quickly have to adapt to it or you can't understand what the F they're talking about. Okay, so before we go any further, let's say this. So let's put some big stars here in gamma ray purple. Okay, so we've got wavelength, that's a concept. We've got frequency, that's a concept. And there's one more I need to squeeze in here. Energy. So our third major property of waves that we want to study is capital E, energy. And of course, in the MKS system, you guys remember MKS units, right? Someone tell me what MKS means so I know that I'm talking to an enlightened audience here.
Meters, kilograms, seconds.
All right, cool. MKS units are joules, right? A joule is a kilogram meters squared per second squared. But alternative units that people who work in the gamma ray regime use, they tend to use electron volts. 1.6 times 10 to the minus 19 joules. Did we do this last time? This kind of feels familiar. We did this, Kayla, didn't we? I'm kind of covering some old ground here. Son of a bee. Okay. Before we go any further, and before we show you some, before I show you some formulas for these, Tony, I'm loving your whiteboard action. I'm really envious of your whiteboard setup now. If only I had such a thing. Let's share my screen for a moment. I want to show you guys something kind of fun. Somewhere in here, I have a folder of physics Java apps. Did I show this to you guys last time? The radiating charge thing?
Yeah, I think so.
Okay. Right. We can see, here's a proton surrounded by an electric field. We can give it a sinusoidal oscillation. I'm going to drop the amplitude a little bit. Watch, as I change the frequency, I'm changing the number of cycles per second. Oh, Jace, you have a question?
I have a weird question, yeah.
Yeah, I like weird questions.
Do the crests of the wavelengths follow hyperbolic or parabolic paths?
Okay, so photons, for the most part, travel in a linear point A to point B direction. If you're asking about the shape of the curve,
Yeah.
the shape of the curve is not hyperbolic, but it's sinusoidal, right? So they obey sine waves or superpositions of sine waves. So let's go back to our mathematics class, right? A sine wave is a pretty well described function. Here's a couple of different sine waves. And all waves are combinations of sines and cosine functions. Believe it or not, hyperbolic functions are also related to sines and cosines, but they're slightly different mathematical beasts. If you look at a hyperbolic functions, hyperbolic functions have a slightly different shape. So I think I'm answering your question correctly. I don't know if I want to say hyperbolic, although one of the tricky things about waves is waves obey something called the superposition principle. And that means that waves can add and subtract to make more complex geometrical waveforms. So I bet if I were to type in superposition principle, this is a big topic in the subject of waves and light as well. Let's see if Wiki has, let me move my little box here. I was hoping they'd have some kind of groovy graphic. Oh yeah, this is what I want right here. Okay. So here you can see a red wave and a blue wave, and they're sliding them back and forth on top of each other to make a, honestly, this is a standing, we could do even better than this. Let's go back to superposition principle, and let's just grab some images here. What I was hoping to show you is some kind of a complex waveform. Like, I don't know if any of you guys, oh, this is the kind of thing that I want to see here. Yeah, if you add different types of waves together, you can get a more complex waveform. Here's two signals being mixed together to make a more complex waveform. Let's say you're into audio editing like I am, right? So audio waveform editor. Sound, like speech and musical instruments, produce very complex sounds. And this is what waves look like inside of an audio editor if you're geeking out in Ableton Live or something and you're making some tunes. But if you zoom in very closely on one of these waveforms, you find that they're a super complex wave that's a mishmash of all types of different sines and cosines added together. It's one of the cool things about waves. They can always be deconstructed as a superposition of really basic sines and cosines. That's the basis of frequency analysis. People do this for light waves. People do it for audio waves. It's a cottage industry, and it's one of the things that we're sort of learning about here. We're taking our first step into that world. Okay, so let's stop the share for a second, and let's learn a couple of formulas. If you guys have your Casio calculators, great time to bust them out. I've got mine here. We can relate these waves to each other by a couple of key formulas, which we're going to need for our homeworks today. They're simple, easy to use basic formulas. I give them little numbers. The first formula is the speed of light is the wavelength of light times the frequency, where c is a constant of nature. 3 times 10 to the 8 meters per second is the measured value for the speed of light in a vacuum. The speed of light in air is quite close to this as well. This number is fixed. It does not change. So let me point out that wavelength and frequency are the two variables here, and the speed of light remains constant. Another formula that we need to learn is the formula that describes the energy of a photon. And the energy of a photon is related to its frequency by another fundamental constant of nature known as Planck's constant. Planck's constant H has a fixed value of 7 times 10 to the minus 34 joules times seconds. And if you want to know what Planck's constant is, it's a wiggy little number that always appears in discussions or calculations involving the world of quantum particles, like protons and electrons, and even photons. Planck's constant weirdly has units that are equivalent to angular momentum, which I have not yet recorded the lecture for. So angular momentum it's about, you know, the constancy of rotation. You might think of Planck's constant as a quantum unit of spin, whereas the spin of my little moon ball can seem smooth and continuous. In reality, at microscopic scales, the spins of objects are choppy and discrete. Planck's constant is a little quantum bit of spin. And you know, this formula was actually developed by Albert Einstein. It's related to an experiment known as the photoelectric effect. And this formula was the only thing that Albert Einstein ever won a Nobel Prize for, not for his theory of relativity. So this tells us that the energy of a photon in joules is related to Planck's constant times its frequency. A simple formula, a beautiful formula. By the way, we might not have spent any time talking about what photons are. This equation is for the energy of a single photon. And that makes me think that we ought to just talk about what the crap is a photon, right? Okay, so a photon is a tiny packet of light. And if I can start off by making a sort of analogy, photons are to light in the same respect as atoms are to matter. If matter, like this 1 kilogram brick, can be thought of as being composed of individual indecomposable units called atoms, light, big beams of light, can be resolved into microscopic bits of light called photons. It's kind of like a localized wave. It has properties that make it like a particle and like a wave. Photons have something called wave-particle duality, and that's a mouthful. Sometimes when people try to draw a photon and represent it, they'll imagine a little wiggle that has a localized packet, something like this, right? And it's still a wave, but the wave is localized in space. Kind of funny. When Isaac Newton first studied light in optics, he believed that light was comprised of microscopic particles called corpuscles. And this might even have been what Newton had imagined a corpuscle to look like. Later on, French scientists were able to show that light had wave-like properties. And for a while, scientists thought, okay, Newton was totally wrong. Screw the particle thing. Light is just a wave phenomenon, and that's it. And then Albert Einstein came back again and said, but you know what? Sometimes photons can behave like little BBs. They have momentum, and they can punch little electrons. And then people said, oh, shit, that's starting to sound like a particle. And eventually, physicists just threw their hands up and said, you know what? Shit, maybe things can be waves and particles at the same time. Is that possible? I don't know. That's crazy. I mean, normally, what makes a particle is like these are particles, right? There's no superposition principle for particles. I can't smush the red ball into the blue ball and create a bigger ball. They won't occupy the same space, but photons can. They can interact by the superposition principle. I don't know. Nature's weird, man. Okay, there's a third formula that sometimes comes in handy. and it's kind of like a combination of Formula 1 and Formula 2. It's another equation for the energy of a photon. And if you will allow me, equation 3, Planck's constant times the speed of light divided by the wavelength. I love this formula because it expresses the energy of a photon in terms of its wavelength. And as someone who works mostly in the optical regime, I tend to think of light in terms of wavelength. That's what's natural to me. There's a couple of messages that are hidden here. You will notice that energy is inversely proportional to wavelength. And that means the following thing. It means short wavelength is equal to high energy photons, and long wavelength is equal to low energy photons. And please note my extremely symbolic use of color. Yeah? You see what I'm doing there? Okay, cool. All right. Sometimes people refer to long wavelengths as the red end of the spectrum and short wavelengths as the blue end of the spectrum. You might hear me accidentally refer to light in that regard. Okay, should we do a sample problem or two? We're going to be doing this for our homework today. Let's start with my green laser here. Let me go back a bit because I'm getting a little squeezed here. Here's an astronomy laser that we can use for pointing out stars. The video camera isn't picking it up, so I wonder what would happen if I just lasered you guys. Whoa, that shit's awesome. Okay, cool. All right, so I know Tony just got blasted there with some laser beams. Now, this green laser is a pure monochromatic source of light. It doesn't look so hot on my crappy old webcam, but I gotta tell you, this green, it's a pure green. It is a single wavelength. What makes laser light cool is they take light of a very unique wavelength and they produce it inside of atoms and they build it up inside of a little cavity here, and the beam that comes out is a very narrow beam of a very pure wavelength. When something is a single color, we call it monochromatic, one color, right? And you guys can see here, if my webcam will pick it up, they list the wavelength right here. Oh, shit. We can't read the fine print, but I'll have to read it for you. It tells you in the fine print that the wavelength of this laser is 532 nanometers. So let's just do a boring exercise here. And let's calculate the energy and the frequency of a single photon of green laser light. And remind me to do the radio wave problem too. Okay. So find the frequency and the energy of a green laser photon whose wavelength is 532 nanometers. How's the readability of this stuff, guys? I know my camera is crap. I bought a new one, but it's taken a while to come in on Amazon. You're seeing that good, Kayla? Okay. Okay, so which formula do you want? Do you want Formula 1, Formula 2, or Formula 3? Let's start with the frequency first. Talk to me, people. I'm getting lonely here in my apartment.
Formula 2.
Okay, Jace, Formula 2 was the energy of a photon. Oh, crap. I don't know, Jace. This certainly would help me find the energy if I know the frequency, but you weren't given the frequency. You were given the wavelength, right?
So 3.
Well,
That doesn't solve for frequency.
we could use Formula 3 to get the energy, but let's do that next. Let's go in order. Let's do frequency first and then energy. I don't know why, but.
Why don't we use 1 and then, do some quick algebra and.
Man, Tony, with all your slick whiteboard action here, I feel like we should go to speaker view and check out your algebra moves. I happen to know that Tony does some math tutoring. So Tony, what I'm gonna do is I'm gonna lock my speaker view on you, okay? So let's see you do some algebra there and help us write it real big because we can't see you writing that well. write it super big or bring your laptop closer. Start off with that formula and help us rearrange it algebra-wise for frequency. Why do you have such a nice whiteboard and I don't? What's going on there? Your head's kind of in the way, but all right, I can kind of see that. All right, now solve it for frequency. I'm getting nervous, Tony. It looks like you're trying to put the frequency on the bottom, right? I mean, Tony, each of these letters are being divided by 1. Let me go back to my view for a second. I'm getting nervous because I see Tony taking the frequency and trying to put it down there. That's going to leave me with 1 over frequency. Why don't we leave the frequency in the numerator where it belongs and push the wavelength to the other side instead? Where are you? Shoot, Tony, I lost you in my little view here. What do you come up with? Yeah, there we go. That's what I'm talking about. C, the speed of light, divided by wavelength is equal to frequency. Smooth moves, dude. Okay, let's see what he did there. He put the wavelength down to get C divided by wavelength is equal to frequency. I can solve for a variable on the right-hand side. That's weird, but you know, I'm weird, so I'm okay with that. Okay, so now we'll sort of plug in our values here. Since we're dealing with a green photon, I should probably use green for my units. So I've got 3 times 10 to the 8 meters per second. What am I going to put in the bottom, students?
532 nanometers.
Who said that? Where are you? Was that Chrissy?
Samantha.
Oh, that was Samantha. Oh, Samantha, I can't see you. You're hidden. Okay, because you're troll. Okay. No, yes, but here's the issue. Samantha, 532 nanometers, that ain't gonna work for me because nanometers and meters are different units of length. So what are we gonna have to do, Samantha? You're about to regret speaking up. I'm gonna make sure you regret it.
I already do regret it. We have to convert it, no?
Yes, convert it to what? To what units?
Well, you're making me go all the way to the end, huh? I don't, meters per second? Meters?
Whoa, hold on. I'm saying we should do everything in MKS units. Your speed of light is in MKS units, meters per second. What I'm not digging is your nanometer moves. So what's the problem? What do I need to do here?
Oh, make it meters.
Okay, so tell me, what's the technique we use to do that?
I don't know what it's called, but you convert it from nanometers to...
All right, so tell me how to do it then. It's called dimensional analysis.
There you go, dimensional analysis.
You never forget dimensional analysis. That's like our man in the basket there.
You have to do the division bar. You do 532.
Wait, division bar is step 2. What's step 1? You got to romance me before you take me upstairs. You know what I'm saying?
0 to 100 real quick.
Okay. What's the first step of dimensional analysis?
You have to write down 532 nanometers.
Thank you. Okay. All right, and then we can put in our division. Then we can put in our division bar, right?
Correct.
Okay. All right, and now what do I do?
You put meters on the top, nanometers on the bottom.
Correct. And that's how our little nanometers get executed. They're done. All right, and now our conversion factor. What's our conversion factor?
Is it 10 to the negative 9? 1 meter is, am I way off?
Well, I just don't know what you're trying to put on top and what you're trying to put on bottom because you have to be.
Oh, on the bottom you would put 10 to the, I don't know.
Let's write down our conversion factor up here. Do you have the conversion factor from earlier in our notes? I thought I gave it to you. Maybe last class.
I wrote it down, but my notes are all over the place.
Well, that's a problem.
1 nanometer is equal to 10 to the negative 9. So is that, I guess I didn't write
Wait,
down
10 to the negative 9 what? You got to finish the job here.
meters?
That's right. Okay, you know what? Astronomers like to do things like this. They like to just write 10 to the minus 9, but that's bad for you little baby astronomers. I probably should have written this out as 1 times 10 to the minus 9. Okay, I agree with you, Samantha. That's your conversion factor. Now tell me a number on top and a number on bottom. Be very specific about it.
10 to the negative 9 is going to go on top, and then 1 will go on the bottom.
Thank you. You are a good dimensional analyzer. Okay, now, you don't really need your calculator for this jobby. You want to know why? Because, Samantha, I bet you know what 532 times 1 is.
532.
Okay, but then what else do I have to include?
Times 10 to the negative 9.
And my units?
Meters. Meters.
Booyah. That's what we need to put into there, okay?
Okay.
So let's do this again. I'll take my moves up to the top here. Let's keep all that handy. All right, so I'm going to rewrite this again. Notes are about to go away here. Yeah. I'm going to write that the frequency is equal to 3 times 10 to the 8 meters per second divided by 532 nanometers. In fact, that's what a nanometer is, 532 billionths of a meter. Hell, if you were real slick, I might even let you, from time to time, just replace the word nano with 10 to the minus 9. That's kind of crazy talk. Okay, kids, punch them up. It's calculator time. That's your job. I already have a job. That's because I did my calculator work when I was a student, and now I'm employed. One day. All right. For those in the studio audience who do not have Casio calculators, hold on, let me get some light on this thing here. Damn solar-powered calculators. All right, here we go. So we're going to do 3 exp8, right? Divided by 532 exp negative key 9. Boom. What's my answer? Someone shout me out.
5.6.
Okay. You're not forgetting something. 5.6 what?
Times 10 to the 14 hertz.
Yeah. Let's not forget about them 14 zeros, right? That's not cool. And yes, Jace, it is units of hertz, but let's start off by doing this slow. Meters cancel with meters, leaving us with 1 over seconds, which Jace has correctly interpreted as 5.6 times 10 to the 14 hertz. You can write either cycles per second or hertz, whichever you like. All right, we did that one painfully slow. Did everyone follow that? Give me some thumbs up if you understand what's going on. Can I get a thumbs up from the Pikachu, Thomas? All right, yeah, thanks. Okay. Loving the Pikachu. All right, that's our first job. What's our second job? Find the energy. What formula do I want to use to find the energy?
Now you want to use equation number 2, right?
Ah, that sounds good. Okay, so equation number 2 tells us that the energy of a photon is Planck's constant times the frequency. We've already got everything in our MKS units right here. I remember Planck's constant, 7 times 10 to the minus 34 joules times seconds. If you were a fan of the TV show Stranger Things, you'll remember that in season 2 of Stranger Things, knowing Planck's constant to like 7 decimal places was an important plot point for unlocking a safe or something. Remember that? Kayla knows what I'm talking about. We're a little bit lazier than that. We're just using Planck's constant to 1 digit of precision, but hell, well, okay, let's not get sidetracked here. Okay, let's put in our frequency next. Times 5.6 times 10 to the 14 per seconds. Punch them up, kids. Punch them up. I've got to stop writing so sideways. It doesn't look so slanted in my room, but on the screen it looks like I got a case of the dropsy here. Anyone? 7, you guys are slow. Negative 34 times 5.6 exp14 equals, what you get?
3.92 times 10 to the negative 19.
Okay. What are my units?
Is it just joules?
Yeah. Now look, that's our answer, but I want us to do something else. Joules are a really crappy unit to use when you're trying to talk about the energy contained in a single photon of visible light. For this reason, we've invented the electron volt as a more appropriate unit. Just for kicks and giggles, let's go ahead and convert this into electron volts using, what do we call that technique again, Samantha, that I use to convert stuff? I
don't know, dimensional analysis?
Hell yes, okay. So we'll start with the number that we want to convert, 3.2 times 10 to the minus 19 joules. I'm going to do the work for you. I'm going to do the division bar and put the units in. We got joules on the bottom, electron volts on top. That kills it. What's the conversion factor to electron volts? Anyone remember? I had this professor once. He said, yeah, memorization sucks, but if you have to look up 2 times 2 equals 4 every time, then you're probably screwed at life, right? What's the conversion?
1.6 times 10 to the negative 19 joules, so that's on the bottom, equals 1.
All right. So punch that up and tell me what you get, someone. I'm tired of calculating. That's a you job. I'm just going to take a moment to look at all your faces hard at work. Look at all those. Hey, Tony, look at all those people calculating.
Would it be
Shout out to my friend Catherine, who's watching from Florida. What's that?
Would it be 6.3 times 10 to 18?
Hell no. Oh, wait, who said that? Was that you, Thomas? Was that Pikachu?
Yeah.
Thomas, here's why I don't like that. Let me get my, you're making me bust out the pointer stick here. Shit's getting real in my home here.
Ooh.
Okay.
All right.
I don't like the fact that you are essentially, remember, this is a times, but this is on the bottom. You're dividing 10 to the minus 19 by 10 to the minus 19. That should be like,
It's 2.
yeah. Well, give me 2 sig figs just for the hell of it. Actually, no, don't. Give me 1 sig fig. I like it. What did you say? It's 2 what?
0.0.
Oh, okay, fine. Hell if it is. But what are the units?
Electrovolts.
Electron volts. This is why electron volts are a cool unit of energy. It turns out that within the visible domain of light, the energies of visible light photons range from about 1 electron volt somewhere near purple up to about 7 electron volts near red. So the energy contained in visible light photons is always a number between 1 and 10 in electron volts. That's one of the reasons why people like the units electron volts. It's going to turn out that these are also approximately the same energies contained in atomic transitions, which I need to get to today. I'm going as slow as damned molasses here. It's already 12:38. Oh my God, I'm so screwed. Okay. In fact, let's get back around to atoms for a second. Now, look, you guys, that was some slow maneuvering here, but we can speed things up a little bit. I want to talk to you guys about the production of an emission line. Here's where things are going to get interesting. Do you remember the hydrogen atom? What's a hydrogen atom comprised of? Tell me about a hydrogen atom. That's important to me.
1 proton, 1 electron.
Boom. Hold on. Control F5. Oh my, no. I just want to slide. None of my things are working. Slideshow. Function F5. There we go. 12. There we go. A basic, what's the name of this isotope again? Try to remember the name of that isotope.
Protium?
Protium, very good. Let's start with a protium atom. And bear with me here, we're gonna do something weird. We're gonna compute something known as an emission line. An emission line is a photon of unique wavelength, frequency, and energy that's produced when an electron drops from a high orbit to a low orbit inside of an atom, as seen here in slide 13. So here you can see a little model of the production of a single photon. An electron finds itself in a high orbital energy state. It drops to a low energy state, and the energy is released. Where's my animation here? My screen is frozen. There we go. And when it drops from high to low energy, it's going to produce a photon of unique wavelength, frequency, and energy. And we're going to calculate it. We're basically going to do the same thing we did before, but now for a much cooler, more noble purpose. This emission line is a very famous emission line in astronomy, as you're about to find out why. It's known as the 3-to-2 transition of hydrogen. It could be one of the most famous photons in the entire electromagnetic spectrum as far as astronomers are concerned. And let's draw our picture here of how this emission line came to be. One day there was a hydrogen atom floating in space, and for some reason, its ground state was unoccupied by the electron. The electron was missing from its home territory, the ground state or the n=1 state. Nor was the electron to be found in the n=2 orbit, but for some weird reason, our electron found itself in the third orbit, the so-called n=3 state. How'd it get there? I don't know, maybe this hydrogen atom got knocked into by another hydrogen atom, and that electron got kicked up there. And that electron's been hovering around, I don't know, for a time of about 10 to the minus 8 seconds or so. And after 10 to the minus 8 seconds, the electron got tired, and it's going to drop from a high orbit to a low orbit. And when it does this, it's going to release a tiny little packet of energy that will express itself as an emitted photon of unique wavelength, frequency, and energy. Our job is to start with the energy and to calculate the wavelength. Now, I'm going to share my screen here again, and we're going to go to our PowerPoint slideshow. Come on, baby. And these are the so-called energy levels of a hydrogen atom as expressed as a sort of rung ladder diagram, showing you the potential energy that the electron has to have to get to each of these states. Now tell me, students, what is the energy that will be released when Mr. Electron drops from orbit 3? Whoa, Nelly. Hold on, can we go back there? I just hit. How much energy is released when the electron drops from the n=3 to the n=2 state? All right, does anyone understand my question?
2.1 electron volts.
Yeah, so 12.1 eV minus 10.2 eV. Wait, 2.1? Do that math again.
1.9.
1.9. Today I'm going to do something that's a little more special, a little more rich than our average calculation. Normally, one or two significant figures would suffice for most of our calculations. But I want to do this a little fancier today. I'm actually going to make it 1.905 electron volts. I'm pretty sure that's what I need to make this work. Let me just test that out again.
Why is it 1.9?
1.0. 12.1 minus 10.2
Okay.
equals 1.9. Am I correct, Jace?
Yeah. I
Okay.
was just confused. Sorry.
Yeah, dude, arithmetic, I find that to be the hardest math. So totally understand. Let me just make sure that what I'm doing here actually makes sense. Sorry. exp negative 34 times exp. Sorry. Bear with me, guys. I'm just figuring something out. Oh, gosh. All right, let's just see what happens. I'm getting myself confused here. All right. Our job is to convert this to joules and then to get the wavelength and the frequency. So how do I convert that to joules? What's my conversion factor?
So you do 1 at the bottom
Uh-huh.
and 1.6 times 10 to the negative 19 for the joules on the top.
Fine, punch it up for me.
I got 3.048 times 10 to the negative 19.
Say that again?
3.048 times 10 to the negative 19 joules.
Can someone else confirm that for me?
I got that too.
All right. I sure hope I did this right here. Okay, so what am I trying to do here? What's my motivation as a character? Does anyone know what I'm trying to do?
Find frequency and wavelength.
Yeah. Screw the frequency. Frequencies for radio astronomers. Those guys are total hams. What about the wavelength? Which formula should I use to get the wavelength? Which formula?
E equals H times F.
We don't have the frequency, right?
Well, yeah, I was going to say if you want to say screw frequency, then what you want to go with is the last one, the E equals H times C over lambda.
Yes, that's exactly right. Okay, I need to ask you guys for a favor. I made a mistake here, and I finally figured out what it was. I need this to be 895. Can you guys just punch that up one more time? I remembered it wrong. It's not one, it's 1.895. My brain must not be working well. Too much whiskey is left over in it from last night, so I couldn't remember the exact number of electron volts. Can we recalculate this energy to 4 sig figs, for instance? Deeply apologize. There's a reason I'm getting all crazy about the 4th significant figure here.
Is it 3.032 times 10 to the negative 19?
That's what I want. Can someone else confirm that? Because anyone can make a mistake.
I got
Apparently even me, which is hard to believe.
I got
Okay. Yeah, all right. Now, we're deciding we're going to use the third formula. The third formula is energy is Planck's constant times the speed of light divided by wavelength. We're a little pressed for time, so I'm going to do the algebra for us. I'm going to flip the wavelength up to the top. I'm going to drop the energy down to the bottom. Flipping a math equation is like flipping a burger. If you can flip a burger, you can do algebra, okay? It doesn't take any special skills. And that means our new equation is wavelength is Planck's constant times the frequency divided by the energy E. Now, remember I talked about that Stranger Things plot point with Planck's constant? Today we're going to need a couple of extra digits of Planck's constant. Let's share my screen with you here. Normally I just lie to you because I love lying to children and students. They don't know any better, so I can just kind of say anything and they think I'm telling them the truth. So I've told you that Planck's constant is just 7 times 10 to the minus 34 joule seconds. That's what I meant. You can see here, this could have been, that Planck's constant has quite a few digits more of precision as measured out by the Bureau of Standards and Measurements here. We're going to go with 3 sig figs. We're going to grab 6.63. Normally 7 is fine for our calculations, but I'm trying to do something a little more rich here, something a little more precise than our average backyard calculation. So we're going to plug in, I'll use my units in red, 6.63 times 10 to the negative 34 joule seconds times, by the way, the speed of light is actually 3.00. It's 3 times 10 to the 8 meters per second, and that's good to 2 significant figures. And that's divided by 3.032 times 10 to the minus 19 joules. Guys, I want our final answer to 3 sig figs. Hit me one time. I can see Kayla hard at work punching in the numbers. I'm just going to take a moment to look at all your faces. Look at all these hardworking students. Makes me very happy. What'd you get, Kayla?
I got 6.56 times 10 to the negative 7.
And what are the units?
I think it's times 10 to the negative 17. That's what I got.
I think it's
everything's the same though.
Did I put any? Negative 34, positive 8, right? Negative 19. Jace, you forgot a number somewhere. It's negative 7. What are my units, though? Can someone give me some units here?
Would it be meters?
Hell yeah, because joules cancel with joules, seconds cancel with per seconds, meters. Okay, now I'm going to ask you a very adult question. In what regime of the electromagnetic spectrum is a photon of wavelength 6.56 times 10 to the minus 7 meters to be found? In what regime, this is what I will ask you on a test, for instance. In what regime of the electromagnetic spectrum is such a photon to be found? Let's go to our EM spectrum slide. If you are, remember, you can get all these slides off Blackboard. 63. This turns out to be a particularly helpful slide.
You want me to take a stab at it?
Well, you glitched on me there. Can you say that again? Was that Tony?
Yeah, I'll take a stab at it. I'm going to say infrared.
How'd you get infrared?
So I know that a millimeter is 10 to the negative 6 meters, and a micrometer.
But that's less than a micron. Remember, you're dealing with negative powers. That's Tony. If you're gonna play that game on me there, hold on. Let me stop my share for a second. Tony, if you put these into microns, you'd have to go to 0.656 times 10 to the minus 6 meters. You're talking about 0.656 microns. You did it backwards because you were dealing with tiny numbers. I got a better idea. Let's slide the decimal place. Look, y'all made a rookie-ass, well, actually, no. Tony didn't make a rookie-ass move. He at least thought to try to convert it to another unit like microns. The first test of that question was, are you wise enough to say, I don't know what the hell that is in meters. I should convert it to a unit like nanometers. Tony chose microns, but Tony's weird. You know, he does weird stuff like that. Noble effort, but you botched it. Let's go in the other direction here. What if instead I instead did this? can you see what I'm doing here? I guess you can. What if I move the decimal place 2 more digits that way? Then it would become 656 times 10 to the minus 9 nanometers. Oh, sorry. I'm botching my job here. That's meters, right? Which is our final answer, 656 nanometers. Students,
Can I
ask
try to
the question
redeem
again.
myself?
I'm sorry? Say that?
Can I redeem myself?
Yes, redeem yourself, Tony.
So I'm going to say it's somewhere in orange or yellow.
Not bad. Not well. So what's the regime? What's the regime of the electromagnetic spectrum called?
It's going to be in the visible light spectrum.
It is in the visible light spectrum. Bravo. Now, let's take a look at a slightly better. That slide that I showed you was okay. Hold on. Let me stand. Could I stand up now, please? As they say in Monty Python. Let me back up. Let me share screen. Let me not show you this, but let me go you know, whoever made this little cartoon illustration of the visible light spectrum, that was some illustration student. That was one of our weed-smoking artist friends. They don't always pay close attention to things because they're high on weed all day, and they don't know what's going on. But if you look at a slightly more precise version of the visible spectrum, here we go. Tony, try that again. 656 nanometers. What color is that photon? Oh, Tony? I can't hear you, Tony. You're muted.
Ask another person and not going to get this.
No, Tony, you had this. You were doing great. 656 nanometers. Can you see my screen?
Yes, but to me that looks.
Oh, are you colorblind?
Something. Yeah.
Shoot, I forgot about that. You know, color blindness affects a lot of men. Here's what I would say. 656 nanometers, okay? So this is 700, so this is 660. 656 nanometers is like right there. I think that's pretty red, but now you got me guessing myself.
I see red.
You see red? All right, someone back. Let's get a woman's perspective here. They have better color vision and discrimination than we do. This is certainly kind of orange, but 656 nanometers is as red as the day is long. That's a red-assed photon. Now, while we're sharing screens here and all, I want to show you guys something else. Let me introduce you to a friend of mine, okay? So somewhere out in the void of space is a cluster of stars and gas known as the Rosette Nebula. And the Rosette Nebula is actually a cloud of hydrogen gas floating in the void of space. Let's close a few of our tabs here. Come on, Google, give me the juice. All right, let's go to images. And here we go. Here's a beautiful astronomy picture of the day of the Rosette Nebula. Look how gorgeous this thing is. Now, the Rosette Nebula is a massive cloud of hydrogen gas surrounding a cluster of newborn baby stars. You can see how blue most of these stars are. I happen to know that these are very hot stars that pump out a lot of ultraviolet light. And that UV light, it goes ripping out into the surrounding nebula, and it heats up the hydrogen gas, and it gets all of their electrons to jump up to the n=3 orbit, where they dingle-dangle around the hydrogen atom for 10 to the minus 8 seconds or so, and then all of the electrons all start to cascade and drop from orbit 3 to orbit 2. And when they do, they emit a single monochromatic red light of exactly 656 nanometers. It's an emission line associated with hydrogen. We call it hydrogen alpha. This nebula, my friends, is kind of like a laser nebula. It's every bit as unique as the monochromatic light source that came out of my laser. And it's associated with hydrogen. Now, I'm pretty much out of time here. I just realized how long I've been talking and boring you all with my stories of astronomy. But let me just show you what we're talking about here because it's related to our labs. In this slide, in slide 15, you can see that there are, now this is a techie looking graph, or photo or illustration here, but just go with me. In this graphic, we can see a whole bunch of different energy levels associated with hydrogen. Can you guys see my mouse as I move it around? You see my mouse? Okay. You just calculated the wavelength of the red emission line produced by hydrogen when an electron drops from orbit 3 to orbit 2. It produces a unique photon at 656 nanometers. It's probably the most famous photon in astronomy. We give it its own name. It's called hydrogen alpha. Now, hydrogen can also produce some other emission lines during different types of atomic transitions. For instance, when an electron gets kicked up to orbit 4 and it drops down to orbit 2, it produces a photon that's extremely blue, 486 nanometers. Astronomers refer to this as hydrogen beta. And there's a third purple photon called hydrogen gamma. 434 434 nanometers are produced when an electron drops from orbit 5 to orbit 2. And these are the three emission lines that hydrogen produces in the visible spectrum. You'll also notice that hydrogen can produce other types of photons outside the visible spectrum. For instance, consider the 2-to-1 transition. After my electron drops down to orbit 2, eventually it will drop down from orbit 2 to the ground state, and it emits a photon at 122 nanometers. Class, in what regime of the electromagnetic spectrum is 122 nanometer light?
Ultraviolet.
Ultraviolet.
Yeah. And check this out. If I go back to Google, right, and I look at the Rosette Nebula, but now in ultraviolet, Rosette Nebula UV, we have ultraviolet telescopes. And when you look at this same nebula in the ultraviolet, it's totally different looking. Instead, we're not seeing the hydrogen alpha emissions. We're seeing the gas radiating the 2-to-1 transition. It's like we're peering into the nebula with a new set of eyes because we're tuning into a different emission line. And this is kind of the heart of the science called spectroscopy. Astronomers study the wavelengths of light emitted by gaseous nebulae in space, and knowing the wavelengths allows us to determine what the elements are that are emitting this light. And this is not just used in astronomy, by the way. It's much bigger than that. Physicists, chemists, hell, even FBI forensic analysts use spectroscopy to analyze blood stains and figure out what types of drugs were in your system when you tried to shoot the president or something like that. Okay, so this is the thing that people do as part of many different career paths. Boy, if the NSA was listening to that, sorry, just kidding, bad joke. Okay, so anyways, what we're going to do here is we're going to go back to the Rosette Nebula before I get the FBI knocking on my door. And I'm going to show you one last thing, and this is related to our lab that we're about to do. Now, it turns out that every element in the periodic table emits a unique set of emission lines. And what we're going to do for our labs in just a couple of minutes is I'm going to use a tool that's very much like a prism. It's called a spectroscope. And I'll show it to you in a moment on my phone. And we're going to look at a bunch of different elements to see what types of emission lines they produce. And I'm going to tell you the tools you're going to need for that, okay? First of all, I just want to test your knowledge of color theory. So function F5, slide 15. Class, if I heat up some pure hydrogen gas, it's going to emit hydrogen alpha, hydrogen beta, and hydrogen gamma photons. And they'll all blend together to make a single color. So what color do you think you'll get if you mix red and blue and violet? Red plus blue makes?
Purple.
Purple plus purple makes?
More purple.
Hell yeah. So let's share our screen, share our iPhone for a second. Bear with me here. Hold on. Go slow for the old man using the technology. Whew. Oh, let's do this again. Okay. This is not what's supposed to happen. I want to go to my camera. There we go. Okay. So can you guys see? Get the hell out of there. Okay. Can you guys see what's going on through my phone here? Okay.
Yep.
Here is a tube of pure hydrogen gas, actually you'll notice that it's actually deuterium, but that's okay because deuterium is still hydrogen, right? Let's move over here so you guys can see what's going on. I've got a high-tech setup here with a cardboard box and a brick of granite, okay? And here's my spectroscope. And here's my hydrogen gas tube. Hold on. I guess I gotta plug it in. Oh shit, wrong switch. And check it out. There's your heated up hydrogen gas right there. Looks pretty darn purple, right? Shall we look to the spectroscope to see what we see? Okay, let's go in here. Oh yeah. Let's see if this works, because this is the premise of our entire lab today. Give it a moment to focus. What do you see?
Red, green, and blue.
Yeah. You want to know what the green is? The green is contamination from trace other elements. But you could see that really pure, that hydrogen alpha line, correct? In fact, you can see it here. I took a photo of it earlier. So the red line is hydrogen alpha. You can see the strong blue line, hydrogen beta, and you can see the hydrogen gamma. Unfortunately, because hydrogen is a very light and volatile element, it's very hard to isolate it from other gases. And I think all that, can you guys see my mouse as I wiggle it around here? Oh, cool. All these green lines are actually contamination. We want the red line, the blue line, and the purple line. The tube that I grabbed quickly during the COVID-19 pandemic, one of our hydrogen tubes is contaminated and the other one is not. I unfortunately grabbed the contaminated one. Okay, so whatever. Let's just talk about what we're about to do, because I've got to stop this lecture and we're going to start our lab in a few seconds. And I apologize, I went over it a little bit. Hydrogen emission lines get me excited. What can I say? Here's our plan, okay? I'm going to give us all like a 5-minute break while I get a drink of iced tea and set some things up. We're going to attempt to do our spectroscopy lab. I'm going to keep it short and simple. Now, we're going to need to make a printout of our spectroscopy lab. And let me close this. Let me share screen once again. And let's go over to, oops, sorry. That's my iPhone share screen. Share screen. Here we go. Here's what I need you guys to do in our 5-minute break or so. I need you to go to Blackboard if you haven't done so already. I need you to go to the lab section. We are going to attempt to do lab 7 spectroscopy. And can you see there that I've provided you with spectroscopy.pdf? It's just one sheet. This is what you're going to need. Now I'm going to hit print. Let's hope to God that my printer works. I think that's what I want.
If we have the lab book, is it in that?
Oh yeah, you can see that it's 11-5. And that should print in my printer. And I'm gonna do it along with you. Okay, by the way, can we talk about strategies here? Let's say you don't have a printer. If you can open that, or let's say you use your lab book if you have your lab book. Print out that sheet if you have a printer. If you don't, you could either try to take a digital image of it, it's a PDF, and you could open it up in MS Paint and you could draw the lines in your favorite visual editor like Photoshop or Illustrator, or if you don't have those fancy programs, just frick it, use MS Paint, right? Another option could be that you could actually draw this out if you were ambitious. You could try to make some tick marks and kind of write this on a piece of paper. In any case, you're going to have to put some colored lines on this thing, and you're going to have to send it to me. Are we all cool with that? Anyone foreseeing any major issues that I should know about? Can you figure it out and make it happen here over the internet?
I drew myself a new one because I used it last semester.
Okay. Yeah, Chrissy, that's awesome. Hold that up. Let me go up to speak for you. Hold that up nice and big. Oh, look at you. Now that's the kind of that's the kind of thing we need there. That's the kind of ingenuity that's required. So, Chrissy, we're not going to do all the elements we did last semester because we're doing it over the internet here. Remember, students, that we also have 3 homework problems to solve. So here's my plan. We're going to look at the elements hydrogen and maybe neon, and I'll show you an incandescent bulb in the solar spectrum, and that'll be it. Sound like a plan? Okay.
So I don't
is
think
that
I
on?
have colored pencils. So like, can I just do like in a regular pencil?
Who's talking to me right now?
Kirill.
Oh, Kirill, I see, you're trolling. Kirill, if you don't have colored pencils or crayons or colored pens, you could just use human blood. You could prick your finger. No, I'm just kidding. What about, so the thing is, the color is kind of an important part of it. So I guess you could use pencil and you could write the names of the colors above it, and that will have to do. But man, it would be cool if you could, you don't have like MS Paint or something where you could make some lines? Maybe that's kind of a pain in the butt. I don't know.
You have Photoshop?
Kirill, you
No.
talking to me? Maybe he's looking for colored pencils. Okay, whatever. Kirill, I don't care about you anymore. Look, if you're in a pinch like Kirill, go ahead and draw the lines in pencil, but you need to write the names of the colors. And I want to hear some ingenuitive, you better bust out the 64 Crayola crayon box in your mind and give me some very vivid descriptions of hues. I want to be hearing about tangerine orange and rose petal red and stuff, okay? So if you have to use pencil, I won't take off points, but my soul will be sad, okay? Because part of this is about color. What's that?
I have paint.
Like house paint? Or,
No.
oh,
No, like the app.
Oh yeah. So try that. If you can handle MS Paint, you could just take the PDF and they can make little lines and go over it. I need a break. Okay, Samantha. Yeah, me too. All right, let's take a 5 or 10 minute pause and then we'll come back. I'm stopping the recording.